Alright guys, in this video I'll be talking about Schrodinger's time-independent wave equation. The fact of the matter is that in classical mechanics, the basic equation, the basic formulated equation we have is Newton's second law of motion. In fact, the role that's played by Newton's second law of motion in classical mechanics, which is purely an approximation of wave mechanics, the same kind of role is played by Schrodinger's wave equation in wave mechanics. So, if we start with a wave function, and all of us know some of the basic properties of this wave function, the complexity involved in this wave function. This wave function psi can be written as a e to the power of I kx minus omega t. So this is a wave function that we are assigning for a free particle. This particle is not subjected to any kind of external constraint. And this particle is moving along the positive direction of x. And you can see some of the symbols in it. This a refers to the amplitude. This k is the propagation vector. This omega is the angular frequency of this wave function. Now, if I write down this k is 2 pi by lambda. If I multiply this with h bar on both sides, h bar, but this h bar is h by 2. So this h cross k will be 2 pi by lambda dot h by 2 pi. Remove this 2 pi and 2 pi. We'll get, this is h by lambda, this is momentum, so this h cross k will refer to the momentum. Similarly, if I take on omega, this omega is angular frequency, and it must be 2 pi nu. When nu is the linear frequency and omega is the angular frequency. If I multiply this by h cross on both sides, h bar. So what will I get here is h bar omega is 2 pi nu h by 2 pi. This 2 pi and 2 pi will be removed. So h cross omega is simply h nu, where this h nu refers to the energy. So E can be assigned to h bar omega. All right. We want to write down this time-independent Schrodinger's wave equation. So that means time-independent, So the situation is such that this moving particle does not have any dependence on the variation in time. And that's why it's sometimes also called as Schrodinger's steady-state wave equation that we are going to derive here. It would be wrong to say derive, because we cannot derive anything like Newton's second law of motion. But we are just trying to formulate this wave function in terms of a differential equation. So you have a freely moving particle, and the wave function of that freely moving particle is given by this. Now, if I take the derivative, the partial derivative of this wave function with respect to x, what I'll get here is iota k psi. Now, if I take another derivative, I will get del 2 psi upon del x2 is equal to, so it will be the square of this, iota square will be minus, it will be k psi. Now if I give some numbers, if I give this number 1 and I give this number 2, you can see from here this k can be replaced by p by h cross. Now moving on, and using the value of this k in this equation, what we will get del 2 psi upon x2 is equal to, it must be square here, minus square of this. What will be the square of this k? Square of this will be p square divided by h cross square and psi. Now, I would like to further translate this momentum. This momentum, if E is the kinetic energy associated with the moving particle, Ek I will call it, this kinetic energy is 1/2 of mv square, and that can be written as mv whole square divided by 2m. So this Ek will be p square divided by 2m. What does that mean? That means this p square is twice me. So I can use this p square is equal to 2me in this equation. When I do that, what I will obtain is the double derivative of psi with respect to x is minus, this must be k, is minus twice m ek divided by h cross h bar square psi. Now, I can also say that suppose E is the total energy of this freely moving particle, this total energy must be the sum of kinetic energy and potential energy. Suppose V is the potential energy and Ek is the kinetic energy. So what will be the kinetic energy? That will be E minus V. I can use the value of this kinetic energy in this equation. So instead of Ek, I will be using here E minus V. So I will get the double derivative of psi along x will be equal to minus 2m upon h cross square E minus V of psi. So I can further manipulate it and I can write down that this del x2 plus 2m upon h cross h bar square will be E minus V of psi. This equation that's out here, this is the Schrodinger's time independent equation. Now you see, we have achieved this result by assuming a wave function and portraying that wave function on a particle which is freely moving. But the real situations depend on certain constraints. So those constraints can be applied on this differential equation. They can be used as boundary conditions for this on this differential equations. While solving this differential equation for a particular problem, we can execute the boundary conditions of those problems that we would like to have a discussion on, we would like to have some understanding on. So this second order partial differentiation, which is primarily for a free particle moving along x, we can further modify this equation in 3 dimensions, and we can write down this differential equation as h cross h bar square e minus v of psi as a function of x, y, and z is equal to 0. So this is the mathematical formulation of time-independent Schrodinger's wave equation. And for the fact of matter, we know that this double partial derivative along x plus along y plus along z, it is del square. This is also called as Laplacian operator. So, in general, I can write down this time-independent Schrodinger's wave equation in a steady state situation where a particle is moving without any state of constraint, without any state of external force. We can write down this as psi plus 2m by h bar square e minus v psi x, y, and z is equal to 0. So this is how we write down